In this lecture, we'll talk about the applications of hash algorithms. You'll find hashes in many areas of computer science. Hashes are everywhere. They are a critical part of password systems, digital signatures, security certificates, blockchain technology, or even how the ATM of your bank verifies the PIN of your credit card when you want to withdraw some cash. Let's see the most useful use cases. Cryptographic hash functions are very commonly used in password verification. For security reasons, passwords are not stored in clear text. If an attacker was to break into the system and steal the file or the database where passwords are stored, the attacker could then access each user account. A more secure way to store a password is to transform it into data that cannot be converted back into the original password. And this is exactly what hashing does. So instead of saving the clear text password, the system will calculate its hash and store that hash. This is how Linux, Windows, databases, and all other web applications work. Let's see the contents of etc shadow. Let's take a look at this line. This is the saved hash of the password of user Kali. No one can find out what is its password. By the way, there is another dedicated lecture where I have explained in great detail how the Linux system stores the user's passwords. I'd recommend you to watch that video as well. Okay, later when the user wants to authenticate, he will enter his clear text password. The system will immediately calculate the hash of the entered password and compare it to the hash saved in the password file. If the hashes are equal, it means that the user has entered the correct password. Remember that each input, in this case password, has its own unique hash which is deterministic. A wrong password would have given another hash. Sometimes the password is combined to another piece of random data called salt. In this example, this is the salt, and hashed all together. Due to rainbow tables, hashing alone is not sufficient to protect passwords from mass exploitation. There is another section on rainbow tables, and I recommend you to watch those videos as well. Let's move on and talk about file integrity. Hashing is also used to verify the integrity of a file after it has been transferred from one place to another. When downloading an important document, new software, or when updating existing one, you want to ensure that your installation is safe, unaltered, and from a reputable source. Let's imagine you want to install a new Linux distribution on your computer. Normally, you go and download it from a mirror, which is an HTTP server closer to you geographically. It would be easy for a malicious entity to modify the installation kit so that it contains exploits or malware and host it unofficially. To prevent this issue, you'll generate the hash or checksum of your downloaded ISO file and verify that it matches the hash published on the official website. In this example with Kali Linux, this hash. If the hashes are equal, it confirms the ISO file hasn't been tampered with or corrupted. But if they are not equal, it means your downloaded image's integrity is compromised. Maybe it was corrupted during the download process. Remember that if a single bit is different in your downloaded file, the file has a different hash than the one calculated by the development team and published online. Let me show you how this works. I've already downloaded CentOS 8 boot ISO file and I want to check its integrity. It's on my desktop. This is the file. I want to be sure that the file hasn't been tampered with or corrupted. CentOS.org has listed checksum information via HTTPS in the release notes for each software release. My release is 8.19.11, and this is the web page for that release. I will calculate the SHA-256 hash of the downloaded file and then compare the hash to the one published online. If they are the same, I have verified the integrity of the ESO file and I can install it without any risk. SHA-256, sum, and the file. It's calculating the hash. Okay, this is the hash. Let's check it against the hash published online. Okay, it starts with 7FEA, 1322B, and so on. It's the same hash. Another application of hashes is the process of digital signing. Hashing is a critical component of the digital signing process. In fact, the digital signature of a file is the hash of the file encrypted with the private key of the one that signs. Let's take a look at the digital certificate of google.com. We see that the certificate authority signed it by using the same SHA-256 and RSA algorithms. The last application of hashes I'm gonna talk about in this lecture is related to data structures of programming languages. Python dictionaries and sets or Go maps are implemented as hash tables. We won't go deeper into it now. You should only know that they provide constant time lookup and insertion time on average.